Hello everybody, you are welcome to this study. Today we are going to look at some problems in wave. So we start with the first set of questions. The first one there is the distance between two successive troughs is a wave in a wave is 3.5 centimeters. If the wave travels a distance of 31.5 centimeters in 1.5 seconds, calculate the frequency of the wave. The period 2. The periodic pulse travels a distance of 20.0 meters in 1.00 seconds. If its frequency is 2000 Hz, calculate its wavelength. 3. A certain wave has speed 20 meters per second. If the frequency of the wave is 0.25 Hz, calculate the distance between successive crests of the wave. Alright, let's see how we handle this problem. Alright, solution 1, as you can see on screen. Solution 1, that's a solution 1, yes. So, distance between successive troughs. The distance between successive troughs is this one, the wavelength, and that is 3 centimeters. The distance traveled by the wave is x, and that one is this one here, 31 centimeters in time t. So it travels that distance in time t, as you can see, t, and that time t has a value of 1.5 seconds. They say we should find the frequency f. So wave speed is v, and that is given as x over t, as you can see. S over t is the wave speed, and it's a matter of it's a very simple matter to come around here and say x over t is also lambda over capital letter T, the period, and if we put the respective values there, we will arrive at this result. Replace 1 over f as 1 over t, we'll write this as 1 over t, and replace this 1 over t here with f to give this lambda f wavelength. So if we substitute the respective values, 3.5 for wavelengths, 31.5 for x, and 1.5 for time, small t, will make some mathematical arrangement here and arrive at this one. Eventually the answer 6 Hz will be. So that is for this section. It's quite simple. Here we have solution to question 2. So you can see the distance is x, and that is 20 meters per second this time. The frequency is what they gave us also, not lambda, wavelength or lambda. They gave us the time. So if we use frequency and wavelength, why are we using frequency and wavelength? They say we should look for wavelength, so not period, and they gave frequency. So the best wave equation that we need is V equal to S over T, equal to wavelength frequency. So we have to compare these two terms, and if we do that, 20 over 1 is equal to 2000 wavelength, where f is this 2000 and 20 is the what, x, and this t is 1. And so we solve by dividing both sides by what, 2000, or we cross multiply 1 times 2000, that's 2000, then divide both sides by 2000, that will give wavelength as 20 over 2000. In the end we get 0.01 meters as the answer. Thank you for that process. I know you are working it out yourself as learner. Please do well to confirm all the substitution. And here is solution number 3. This time it is the wave speed that is 20, given as 20 meters. Frequency is also given as 0.25, as you can see. Frequency 0.25. So using the straightforward formula, speed is equal to lambda f as frequency times lambda as wavelength. making wavelength subject to formula because that is what is required. I think this is quite straightforward. We get the result, 80 meters. So as a learner, do well to just make the substitution and divide and confirm your answer. Okay, very well. This is another one. Other examples, as you can see, other examples. A wave has an amplitude of 4.0 meters, angular speed of 1 over 3 pi rad per second, and phase angle of 2 pi over 3 rad. So say we should look for the displacement y of the wave particle is given us. They want us to write the wave particle displacement, which is simple. We just need to go and write the general formula for the wave displacement, and then in writing the general formula, the general standard is y equal to a sine omega t minus ks for a progressive wave. That is a wave traveling from left to right. We have the minus sign in between. Please take note of that. It is the minus sign. Omega and k are the constants. Here omega is 2 pi over capital letter T or 2 pi f, as the case may be. But here k is also 2 pi over wavelength, but here they gave us the values directly as phase angle. K times s is phase angle, ks. So wave number times displacement is equal to the phase angle between 2 points in a wave, and they gave us as 2 pi over 3. So ks have been given, not k. So, and they did not want us to really find wavelength, so no need to go and find to evaluate k again. Omega is also given. Here is the omega. Omega is given around there. Omega, look at it. Omega is given 1 over 3, and the amplitude A is given, which is this one in the expression. So we just need to substitute in the general standard, and then we have 4 for amplitude. This one we have 1 pi over 3 for omega. We have 2 pi rad for ks. So that is this minus sign there, this one. So we are substituted for omega and k. So what is common here? Pi is here, pi is here. Take it outside the bracket. 3 is done, 3 is done. Take it outside the bracket. What will remain here will now be t, and here will now be 2. So that is the correct answer to that question. So once again, we have a second question in this group. The equation of certain wave, a progressive wave, pardon me, is this: x and y in centimeters and t in seconds. Calculate the period of the wave. Solution: comparing the standard wave equation, which is y equal to a sine omega t, as we saw earlier on. X is the wave phase angle, or k is the wave number. Okay, pi omega here is the angular velocity or angular speed or frequency, angular frequency. Take note of that. So we come back here and say a sine omega t over period. This 2 pi should be 2 pi over t. We try to take 2 pi outside, all right, and leave t over big T here. So the 2 pi over t replaces omega in this expression. Here we have 1 over wavelength, which means there is a 2 pi on top of this wavelength before, which represents k. So k is 2 pi over wavelength. So we have actually factorized the 2 pi common to these two terms outside the bracket. That is why it's here. And so what we have here is, for ks we have 1 over lambda x, and for omega t we have t over capital letter T, where ks is equal to s over 30 and 1 over t is equal to this part. So we are comparing the t portions and the s portions. They must be equal. So if that is the case, we'll now arrive at the result. T is t in the denominator, in the numerator rather. So capital letter T must correspond to the denominator. So nothing to really solve much, because following the rule of mathematics, we must see that T must be equal to 0.01 seconds. So that is it. Thank you for that. So here is an exercise that the learner is expected to handle. Please, if you have followed this course, please try and do see how you can provide solution to these simple wave equations. There are 4 in total. Please do well to answer them. You can send feedback to me so that I can confirm the correctness of your solution. Do have a nice time out.